I hope all of you are having excellent day. I am Mr. Ish. Thank you for joining me for this video. Recently we've been looking at first order differential equations, particularly with that one case of the linear first order differential equations where we utilize the integration factor technique to solve a differential equation. We have a differential equation right over here. That differential equation is very much to do with this simple circuit you see over here. There's a switch. There's a battery over here which is 9 volt, a 9 volt battery. You have a resistor here which provides a resistance of 2 ohms, and finally you have an inductor over here which has a value here in terms of henries, 2 henries. You don't have to worry too much about what the definitions of resistor or an inductor or inductance or resistance, all of that, because we're not talking about physics. We're looking here purely at a practical application of a differential equation. How is it that these differential equations relate to real life phenomenon? And that's exactly what we're talking about. If you look at this particular equation, you have what appears to be an inductance attached here with the change in current over time. You have a resistance here attached here in terms of a product relationship to current. All of this is equal to your electromotive force, which you can also think of it as the voltage which is going through this simple direct circuit. If you are to look at these values over here, you can plug them in right exactly where you see that, and then we can look at all of this. In this particular equation we have to find IT. What is IT? IT will be the function for which this differential equation is true. Remember, when you solve a differential equation, you're coming at a function or an equation for which that differential equation was true. When you're solving this, you should be arriving at this. What is it exactly that this is? We will find out. Then you have to find in terms of time. In all of these instances, t is equal to time. Time here being measured in seconds. Find the current in this simple direct circuit at 5 seconds, 10 seconds, and at infinity seconds after the switch has been turned on, because here you're seeing the switch is off. When the switch is off at time 0 seconds, you know there's zero current. There's no current in that circuit because the switch is off. But the minute after that very time that the switch is turned on into the on position, you've crossed that 0 second barrier. What is the current that flows in this specific circuit, having a resistance, a certain inductance, utilizing those time values? And let's do that. Let's look at these values and plug them in over there. We have a value here in terms of L equal to 2, you can put it over here. You have 2 di over dt, the change in current over change in time, plus Ri. Here's your resistance value, 2I is equal to ET. What's your ET here? Your electromotive force or your potential over time is right here, 9. It looks very much like something like this. dy over dx plus py is equal to q. Exactly what you have over there, or what you've seen in the previous videos, is what it is shaping up to be. But staying true here to the symbols we have, let's work on this. Remember this part right over here. This part right over here is talking about the drop in voltage as a result of this resistor, because it resists that current passing through it. This portion right here is talking about the drop in the voltage that you see as a result of this inductor, but the combined sum of these drops in the voltage is always equal to the supplied voltage that you see in this simple circuit. Anyhow, let's get to our work over here. The switch has been turned on. We're past that 0 second mark. Let's solve this. You know you're going to do the integrating factor technique, divide everything here by 2, and that's the way to proceed. When you do that, from here you bring it into the form that you're familiar with. You'll have di over dt plus I is equal to 4.5. Now you know it looks very much like dy over dx plus py is equal to q, that linear first order form. That's exactly what you have. There's a certain coefficient right over here, and that coefficient is 1. To find the integration factor, you're doing e with the exponent of integral dt, everything here with respect to time. We're not going to say dx, we'll say dt. The coefficient here, the p value is 1. It's going to be e to the t. That's exactly what it is. That e to the t is now going to multiply across and distribute across this item that you see, and when you open it up, you'll have e to the t di over dt plus e to the ti is equal to 4.5 e to the t. You see all of that. There's nothing here out of the ordinary. We're just doing this entire differential application with regards to something practical. This aspect right here is coming from the implicit differentiation of an item. And what is that? Just look at this I and look at that, and that's exactly what's going to be. I e exponent t is equal to You can look at the integral of everything here, 4.5 e to the power of t. These go away, you'll have I e exponent t is equal to, what's the antiderivative of that? It's not hard. E to the t is just e to the t, 4.5 is just 4.5, it's 4.5 e to the t plus c. That's exactly what it is. You can solve for this particular I, because we're looking for this part right here first, is equal to 4.5, take this e exponent t on the other side, and adjust for the negative exponent, you'll have c e to the minus t. This right here, you can now say is equal to your I, your function. Now we can solve it even better if you look at this particular aspect right here. At time 0, the current is 0 because the switch was originally off, but then we turned it on. So you have 0 is equal to 4.5 plus c e to the power of 0, which is just a 1. C is equal to minus 4.5. Now you can present this answer right here even in a better way, a more meaningful way. Now that you know the value of c, it's a minus 4.5. Your answer here can be 4.5 minus 4.5 e to the minus t. If you want, you can isolate the 4.5 from all of this and parenthesize everything in between. 4.5 exponent 1 minus e to the power of minus t. You don't have to. I'm just going to keep it like that. That right there is your function with respect to time, from which now you can do these calculations. And let's do those calculations. I'm going to do those calculations for you right over here. I'm going to erase all this because you don't need to see it anymore. Let's look at time 5 seconds. You know what you have to do. You put everything right over here into this equation, right over here, and you use your scientific calculator. You'll have 4.5 minus 4.5 e to the exponent minus 5, because that's 5 seconds coming right over here. You bring in your calculator, 5 with a negative, you do the shift exponent e times 4.5, you minus that from 4.5, you'll get 4.469. What will be your units over here? 4.469. Well, the units are here, and with regards to current, it'll be amperes, amps. If you want to write amps, you can do that. It would really be written as a capital A. Anyhow, I, with respect to 10 seconds, it's not going to be hard. You'll do 4.5 minus 4.5 e to the minus 10. You can run it through and you'll see what you get. You'll get a value probably very close to 4.5. Negative 10 exponent with respect to the exponential base, multiplied by 4.5, and this is being added to 4.5, you're getting 4.499. 4.499 amps. You know what I, with respect to infinity time, is going to be when the current is very well established in this circuit. What will be your current? Everything has adjusted and everything is flowing through with no impedance. Your current is going to be exactly with the infinity coming right here in place of time right here. And you don't even have to calculate this because you can do simple mental math here. 4.5 e to the power of minus infinity is the same thing as 4.5 divided by e to the power of infinity. All of this will zero out. It zeroes out because you have such a large number here in the denominator. This zeroes out. It's just going to be 4.5 amps. And that right there will be your answer. We found this function over here for which this differential equation is true, and it's right here utilizing this. Current is 0 amps at 0 seconds. That makes sense. Switch is off. There's no current because it's an open circuit. Once the circuit is closed, electrons are flowing through here. Then at 5 seconds, 10 seconds, and at infinity seconds, we found you the values. Here's one value, here's another one, and here's the other one. And you can see here as the time approaches infinity, your current approaches exactly what it is you're seeing right here at this value right over here. But you don't have to understand why it's approaching that value because this is not physics. This is not a physics lesson by any means. This right here is just basically a practical application of a differential equation, and that's all I wanted to show you in this particular video. How all of that you've seen in the previous videos relates to something like this. You have to be used to seeing equations in other symbols versus just x and y. Here you don't see any x's and y's. Your main variable here is with respect to time, the time here being your independent variable. And that's it for this video. Thank you for watching. Have a great day. Bye.